Hello, my name is Keisteria Battle, and today my partner Crystal Bethards and I will be discussing the following topic of plasmonic solar cells. First, we will give you some background on the history of plasmonic solar cells and why the technology is needed today. Then we will present some important definitions for understanding what we are talking about in this presentation. Then we will talk in detail about the two main types of plasmonic solar cells, nanoparticle cells and metal film cells. Then we will finish the presentation with how the plasmonic solar cells enhance energy absorption and potential advancements in the technology. There are three main reasons why photovoltaic solar cells were invented. The first is the energy shortage. The energy shortage is caused by overconsuming energy. The world is overpopulated. Most energy firms are using outdated equipment. There are few power plants that can fill the hole between demand and supply of energy. We are wasting energy. Accidents such as pipelines are bursting, and wars with other countries are preventing us from having a surplus of energy. The second reason is fossil fuels. Fossil fuels consist mostly of coal, oil, and natural gas. These provide about 85% of all of the energy we are consuming. This is bad because fossil fuels are limited and are polluting the environment by emitting CO2. Fossil fuels are not renewable, which is why solar energy is starting to compete with fossil fuels. Our third reason is that they are more accessible. Solar energy is becoming more accessible to the public. Solar panels are becoming cheaper, and many companies and governments are introducing solar panels. For example, in Marietta, Georgia, the city government has lined the roof of the municipal courthouse with solar panels and have since gave approval for more projects to be conducted because of the impact of the solar panels on the roof. Another example is Tesla, who acquired Solar City in 2016. Since then, they are becoming a competing factor for power companies. This is because they are renting out solar panel systems for about $50 a month, or if you live in California, then $65 a month, and they are doing this without any long-term contracts. In 1839, photovoltaics were first used when a French physicist named Alexandre discovered that light can be converted to electricity. In 1918, a Polish scientist named Jan discovered monocrystalline silicones can be used for solar cell production. In 1941, the first solar cell using silicone monocrystalline was constructed. Early silicone solar photovoltaic cells did not, however, have good efficiencies. Since then, there are 4 different categories for solar cell efficiencies. There are multi-junction / single junction cells, crystalline silicone cells, thin film, and emerging photovoltaics. With the highest solar efficiency at 47.1%, this is a huge advancement considering the first conventional photovoltaic cells were produced in the late 1950s, but in the late 1970s, oil prices rose and solar power demands increased. Plasmonic solar cells is cheaper than most photovoltaic technology. Since it is thinner and more flexible, it costs roughly 50 cents to $1 per watt. Materials, installation, and manufacturing make up the cost for photovoltaic technology, with materials being 40% of the total cost. Plasmonic solar cells will decrease costs by 10%. This is because of the unique structures of plasmonic solar cells. The typical problem with thin film solar cells is the compromise between making the semiconductor layer thick enough to absorb as much energy as possible, but also keep it thin enough to reduce recombination of electrons. With the addition of well-placed metal particles to the typical thin-film solar cell structures, plasmonic solar cells are able to trap light in the absorption layer longer than previous technology allowed, without increasing the thickness of the absorption layer. In this slide, I will discuss basic definitions that will help with the understanding of the rest of the presentation. Plasmons, like photons, are the quantization of the oscillation of light. Plasmons are the quantization of the oscillation of plasma. You can think of them as quasi-particles that oscillate back and forth with the oscillation of electrons that repel away from the positive ions in the metal. They are mainly in metals and are used to concentrate and funnel light using sub-wavelength microstructures. They are also used to obtain true color holographic images. Plasmonic solar cells. Plasmonic solar cells are a type of thin-film solar cells with the addition of metal that have been significantly shaped and placed to increase the absorption of energy. The addition of metal creates oscillation in the semiconductor layer of the solar cell, which allows more time for the light absorption.
The basic structure of a solar cell breaks down into 7 layers of material chosen for specific purposes. The first layer is the transparent conductive coating. It must be transparent enough to let light through it and conductive enough to act as one of the 2 electrodes in the solar cell. The next layer is the anti-reflective coating. It ensures light goes into the cell to be trapped without being reflected away. The third layer is the N-type semiconductor. Typically, the N-type semiconductor is doped with phosphorus, and it acts as a window into the cell. This side of the p-n junction develops an excess of free electrons. We'll come back to the p-n junction, which is the black layer, in a minute. The p-type semiconductor is typically doped with boron and develops an excess of electron holes instead of electrons like the n-type semiconductor. The next layer is the ohmic contact layer. It creates an effective electrode to capture the current created in the cell. The last layer is the substrate. For plasmonic solar cells, glass, plastic, metal, etc. can be used. So back to the magic. The junction formed between 2 semiconductive layers is called the p-n junction. As Casteria mentioned before, one of the problems that we have is the recombination of electrons before we get anything out of them. Free electrons want to combine with holes in other molecules. But if these electrons recombine in the green n-type semiconductor layer, we don't get any energy from it. But when the electrons require enough energy from light and photons entering the cell to jump across the junction to the p-type semiconductor, where there's a buildup of electron holes, they do so. And they create a current in the junction that is then trapped and collected in the solar cell and converted to usable energy for us. So let's dive deeper into the difference between a basic solar cell structure and a plasmonic solar cell structure. There are 2 different types of plasmonic solar cells. One is the nanoparticle plasmonic solar cell, and the other is the metal film plasmonic solar cell. Let's start with the nanoparticles. First, nanoparticles are tiny flecks of shaped metal, usually spheres, that are added to a layer of a solar cell to increase energy absorption. One layer that the nanoparticles are commonly added to is the top of the N-type semiconductor. The addition of nanoparticles at this place in the solar cell allows more light to be scattered into the solar cell. Any light that is reflected off deeper layers without being absorbed has far more of a chance to be reflected again into the solar cell off the bottom of the nanoparticles. The second most common placement of nanoparticles is in the p-n junction, where the most absorption happens. When placed in this layer, the photons hit the nanoparticles and create surface plasmons, like Casteria talked about, on the nanoparticles. These oscillations on and around the nanoparticle allow more time for energy to be absorbed in the cell. As I mentioned before, the other type of plasmonic solar cell is the metal film plasmonic solar cell. In this version, a grooved metal film is placed under the p-type semiconductor and is usually used as the ohmic contact. For this reason, manufacturing is made easier and cheaper with the metal film version. The grooves in the metal film act as a waveguide for the photons and generate surface plasmons. These oscillations allow more energy to be absorbed. So how do any of these designs actually enhance absorption? It all comes down to the amount of time photons stay in the cell and how deep they penetrate. The first nanoparticle cell we talked about creates scatter, which directs more light into the cell without reflecting it away. It basically enhances the anti-reflective layer. The second nanoparticle we discussed creates a concentration of surface plasmons in the absorption part of the cell. You can think of this type of cell as having a ringing bell in that absorption layer. This ringing bell sounds louder right next to it than it does when standing further away. Your ear absorbs more of the oscillating sound waves standing right next to that bell than it does if you stand further away from the bell. Just like that, these ringings happen in the p-n junction. The last cell we talked about creates a longer path length that a photon travels in the cell. It also creates the same surface plasmons that were helpful in the second nanoparticle cell. Again, that ringing back and forth between those grooves allows the energy to be absorbed. One of the potential advancements to the plasmonic solar cell is the use of lattice structures in the metal film instead of just grooves. The lattice structure is already used in various other applications, but the addition here would set up better waveguides in the metal layer. It would potentially allow a wider frequency of light to be absorbed and converted into usable energy. In conclusion, the addition of intelligently shaped metal into the thin film solar cell has greatly increased our capabilities to capture, convert, and use our seemingly infinite supply of clean energy in the form of light. And we look forward to seeing where this advancement takes us in the future. Thank you for your time.
And please see resources used in this presentation. And for further information, please go see any one of the websites used below. Thank you.